All right, so let's first of all talk about what a logarithm is. Okay, you'll notice we have very similar stipulations as to what we did yesterday. A is positive and not 1. That was the same as when we had a to the x power. Okay, so I want to remind you what a logarithm is. I know you've talked about it before. But I want to remind you what a logarithm is. I want to remind you how to use logarithms as far as rewriting them. And then we'll also talk about their graphs, okay, and how they relate to what we talked about yesterday. Okay? All right, so our base, A, okay, that's the base. It always has to be positive. It cannot be 1, okay? If we have a logarithm, raise your hand if you remember how to rewrite a logarithm. I heard the word exponent.
Yeah.
Okay.
Like a little circle thing.
The little circle thing. Our base stays as a base. The logarithm equals a power. Remember that little circle thing? Okay, that. How many of your Algebra 2 teachers did that notation with the circles? Or the arrows, I guess I should say. Okay. So a logarithm is defined as an exponent. Okay? A logarithm is another way of writing what an exponent is. Okay? So if we have y equals log base a of x, that's how we're going to say it, then that's the same thing as a to the y equals x. And since we have this if and only if statement, that means we can go from one form to the other and vice versa. We can go back and forth. Back and forth. Okay? So let's just go to some exponents that we'd be familiar with so we can practice rewriting these things. Okay? Okay, log base 2 of 16 equals 4. Okay. Log base 2 of 16 equals 4. Why is that a true statement? Because 2 to the 4th equals 16. Log base 10 of 10 equals 1. This is something that I want you to be able to recognize very quickly, and we're going to talk about it on the next slide. But log base 10 of 10 equals 1. Okay? Why? Because base 10 raised to the first power equals 10. True statement. Log base 3 of 1 equals 0. This is something else we're going to talk about here in general in a moment. Base 3 raised to the 0 equals 1. 3 to the 0 is 1. So I want to talk about some properties of logarithms. to where we can use them to make our life maybe a little bit easier, okay? Let's also talk about why we have logarithms, okay? All of these work out very nicely, right? Okay. But if we were to have something like 2 to what power equals 3, there is no way for us to figure out what power we can raise 2 to get 3 without a logarithm, right? 2 to the x equals 4, that's nice and pretty. 2 to the x equals 2, that's nice and pretty, okay? We know that x should be between 1 and 2, because 2 to the first is 2, and 2 squared is 4. But without a logarithm, we can't decide what x is in this case. All right? So that's why we're working with logarithms. Let's talk about their properties so we can make, like I said, our life a little bit easier. Okay? Okay, so go ahead and write this down. Log base a of 1 equals blank because. And as you're writing it down, maybe talk at your pod a little bit. What do you think that blank is supposed to be? Log base a of 1 equals blank. What should go there? Have a discussion. All right. Guy, what's in our blank?
0.
Why?
Because anything raised to the power of 0 is 1.
Okay, so anything raised to the 0 power is 1. Is that what you said?
Yes.
Okay. Brayden, what do you think about his logic?
He's right.
You think he is right. Okay. A to the 0 power is 1, therefore log base a of 1 equals 0. Okay? So here's what I want you to do. I want you to be able to recognize that if you have a log base something of 1, okay, without having to go through the rewriting process officially, we can think about it in our head. Oh, hey, that's going to be 0 because I have a 1 inside of my logarithm. This one I really like, and this one will be very useful to us next week when we get into solving. Log base a of a equals what? Talk about it at your pod. What is it and why? Oh, okay, that was quick. Okay, Austin, log base a of a, what is it?
1.
Okay, why?
Because anything raised to the first power is itself.
Okay, anything raised to the first power is itself. Okay, Dallas, do you agree?
Yes.
You do agree. Okay. Sometimes, and we're going to talk about this here. Log base a of a, it's almost like they're undoing each other. Okay. So some of us might even like to think that log base a of a kind of cancel each other out, and we're left with 1. We'll talk about that more officially when we get to our graphs. Okay. Number 3, log base a of a to the x equals what and why? Write it down. Brainstorm with your pod. Make sure you have a reason to back it up. All right. Addison M. What do you guys think back there?
It equals x.
X, okay. What's your reasoning? Okay, if we think about rewriting this, right? Base A raised to the power equals what's inside? A to the x equals A to the x. Kind of like I mentioned before, log base A of A, they undo each other, and then we're left with that exponent of x. Okay? For example, if we had like log base 2 of 4, you could almost think of this as log base 2 of 2 squared. These undo each other, and we're left with 2. Okay? Just a different way to think about things without having to rewrite. Okay? And then our last one. Okay? The last one I'm going to have to kind of help you fill in. You're not really going to, you don't know what to put here. Okay? If log base A of x equals log base A of y. If log base A of x equals log base A of y. What would be true? Kaya?
Would x be equal to y?
Kaya asks, would x be equal to y? Riley, what would you say? Riley,
I agree.
you agree, okay? Makes sense, right? It's kind of like that problem we did from our homework that Emily asked about, okay? Log base A of something equals log base A of something. As long as we have logarithms with the same base with equality, then what's inside better be alike, okay? All right, I'm going to give you a moment to write these down, and then at your table, come up with what these answers are. Okay. So write them down with their answers. I'll give you about a minute, minute and a half to come up with these 4, and then we'll talk about their answers. You can talk to each other. Remember, we are working with logarithms which equal powers. Logarithms equal powers. Okay. All right, let's talk about these answers. Let's talk about these answers. Callie, what do you have for log base 4 of 16?
It equals 2.
2? Good. And Caitlin, why would log base 4 of 16 equal 2?
Because 4 to the power of 2 is 16.
Excellent. Log base 5 of 1. Emily B., what do you have there?
0.
0. And Mara, why would that be 0? Great. 5 to the 0 power is 1. Okay. Let's see. Log base 9 of 3. Log base 9 of 3. Sydney, what do you have for that?
We have -2.
You have -2.
Or 1/2.
Or 1/2. Okay. If we're not sure about an answer for a logarithm, what could we do? Okay, we could rewrite it. Okay. So our base is 9. is 9 to the negative second power 3. Okay, what does a negative power mean? A negative power means we go downstairs. Is 1 over 9 squared 3? Okay, so that's not going to be it. Okay, is 9 to the 1/2 power 3. Well, let's talk about what a fractional power means. 1/2 as a power means what? Square root. So is the square root of 9 3? Yes. Okay, so our answer is 1/2. As I was walking around, I know some of us were tempted to say 1/3, but remember we're talking about powers, and a 1/3 power would be a cube root. Okay, so if that were 27 as our base, that would be a cube root, but since 9 is our base, we need that square root. Okay, all right, let's talk about this last one, log base 3 of -1. Does anybody have an issue with that? Yes? An issue like, I don't know how to answer it, or an issue like a different issue?
Since it's greater than 0.
Ah, we can't have negative numbers in our logarithm. Okay? And I didn't make a big deal out of this in the beginning because I wanted you to kind of think through it a little bit. But Emily just pointed out, we wrote down that what's inside our logarithm has to be bigger than 0. Well, let's talk about why. When we rewrite it as an exponent, can we have a positive number raised to a power equal a negative number? No, we can't. We talked about that yesterday with our exponential functions. So inside of our logarithm, whatever we're plugging in, we can't plug in 0, we can't plug in negative numbers because exponentially, that's not going to make sense. Okay? So anytime you see a negative number inside of your logarithm, that is not going to work. And you need to recognize that that's not going to work. Okay? All right. Let's use our property one last time. Sorry, I'm going to kind of, oh, there we go. Write this one down. I'm just going to bounce all over the place here with my notes. Okay. Monique, you were very excited when I put this example up. Can you tell me what made you so excited?
Because the base is the same.
Nah, we have logarithms that have the same base. And these logarithms that are equal that have the same base, what does that mean about what's inside? They better be the same. So this kind of scary logarithmic equation really turns into what's inside better equal what's inside. Okay? And the reason we can do that, I'll point out again, like Monique said, we have logarithms with the same base. Okay? So now we have a nice linear equation. X equals -2. Okay, yesterday we had a conversation about the number E, right? The number E, and that you all were like, oh, that's such an awkward thing to say. Okay, let's talk about how that works into a logarithm here. Log base E of X we write as the natural log. Okay, E is the natural base. So when it's in a logarithm, we call it the natural log. Okay, and we write it differently. We write it with that ln, natural log. Remember, math was not invented in the English language, so I know that those letters aren't in the order that you want for natural log, but go with it. Pretty much. Yep. Okay, so when you see the natural log, I need you to think, this is log base E. Okay. Okay. Whether you physically write it or think it in your head, you need to put that base E in there. okay? Because if I were to ask you to rewrite something like this, natural log of 10 equals 2.302, okay? Well, then when we go to rewrite it, we need to understand that that base is e, okay? So we have this log base e raised to the 2.302 power equals 10. And then going the other way, e squared is 7.3890. We do our same loop-de-loop the other way. Okay. Here our base is e. Our base is e. Remember, we're not going to write log base e, but we have log base e of 7.3890 equals the exponent 2. Remember, a logarithm will always equal our exponent. Our last portion of class, we are going to focus on logarithmic graphs. Okay. Logarithmic graphs, once again, my expectation is that we do this without a calculator. All right. So just know that whatever we practice up here and what you practice in your homework tonight will be on the non-calculator portion of Friday's quiz. Okay, Friday's quiz will actually be 2 pieces of paper because one piece of paper you're going to use a calculator with, and one piece of paper I'm not going to let you use a calculator with. They're going to be 2 different colors, so I know who should have a calculator on their desk and who can't. But they'll basically be 2 parts to the quiz. Does that make sense? Okay. Same thing will happen when we take the test as well. Okay. So the first thing I want you to think about, y equals 2 to the x and y equals log base 2 of x. I have y equals 2 to the x up here right now. Go ahead and have a conversation at your pod. Is there a relationship between 2 to the x and log base 2 of x? And if there is one, what is that relationship? Go ahead and brainstorm quickly. Okay. Kinley, I heard you having a very interesting conversation. Can you tell all of us what you were talking about?
I was just saying that they have the same base, but since the one says log base 2 of x equals y, if you flip the 2 to the x equals y, you get log base 2 of y equals x.
Okay, so if you were to rewrite this, you would get log base 2 of y equals x. That's what you were saying? Okay, so look at this and look at this. What's true about those two? And why are they inverses?
Well, I put them, the x and y switched.
Okay, from here to here, x and y switch places, right? So we are going to use the fact that they are inverses to help us come up with the graph. Now, because an exponential equation and a logarithmic equation are inverses, that's why, like the log base 2 of 2, they undo each other. Log base 2 of 2 to the x, they undo each other to equal x. Okay, when we have inverses that are composed together, they undo each other. Okay, so when we graph y equals 2 to the x, we graph the coordinates negative 1, 1/2, 0, 1, and 1, 2. Would you agree those are the 3 points that I want you to graph? Okay. So if we're talking about y equals log base 2 of x, we're talking about the inverse. And you just told me what happens with inverses? Their x's and y's switch. So this becomes 1/2 negative 1, 1, 0, and 2, 1. Okay. So now I want you to think about those same 3 coordinates, but we're going to switch x and y. So now our negative 1, 0, 1 will land in the y column. Okay. Instead of a horizontal asymptote, we are now going to have a vertical asymptote at x equals 0 because we have to protect our logarithm. We can't plug in negative numbers to our logarithm. Okay, so that asymptote is protecting us. Okay, don't plug in 0 or below. So let's go ahead and go through a parent function and then talk about a parent function that's been transformed, and then that'll wrap up our day. Okay. First of all, is there anything that I can clarify with this graph up here? Yeah, let's give me a minute for that.
Sorry, I cracked my wrist like pop. And I messed up this one. That's why.
All right. So just to be consistent with yesterday, we are going to graph the parent function y equals log base 3 of x. Whether you want to rewrite this or not, okay, I don't think you need to, but if it helps you, you go for it. But when we graph a logarithmic equation, we know that negative 1, 0, 1 needs to be in the y column of the parent function. Okay? And with all of our work yesterday with exponentials, we know it should go in the x column, but let's just kind of think about it. Okay? If negative 1 is in our y column, that means 3 to the negative first, which would equal 1/3. If 0 is in our y column, 3 to the 0 equals 1. Okay, so I'm still kind of thinking about those exponents. And then here with 1, 3 to the first power is 3. Okay. So those 3 coordinates are going to get graphed. We will draw in our vertical asymptote and label it. So you'll notice, since this is the inverse to 3 to the x, we have that reflection about the line y equals x. Okay, so instead of exponential growth, we've reflected about y equals x, and now it's this logarithmic. Let's talk about domain and range. I can guarantee you that each graph I ask you to complete on the quiz will be accompanied with a domain and range identification. Okay, so you will have an exponential graph where you will identify domain and range, and you will have a logarithmic graph where you will identify domain and range. Okay, so the domain of this graph. Okay, Emma Ralston, what would our domain be?
Would be 0 to
And what makes you choose 0 to start with?
because our asymptotes.
Okay, good. We have an asymptote at x equals 0, and then we have curve after it. Okay, so 0 to infinity. Our range, where do we have y values? Okay, Jessica, where would you describe our y values? Okay, good. RL numbers. You'll also notice, since this is an inverse, these are flip-flops from yesterday. Exponential function has a domain of all real numbers, which means a logarithmic graph is going to have a range of all real numbers. All right, last example. Get excited. Get excited. Okay. I would like you to take the same process as what we talked about yesterday with exponentials. Please think of the parent function and then transform it where you need to go. Okay? So since we have log base 3 of x plus 1, the quantity, plus 2, then your parent function, PF, parent function, is log base 3 of x. Okay? Not a coincidence that that's what we did on the previous slide. But to remind you, I want that negative 1, 0, 1 in the y column now of our parent function. And then we can fill in the x column with the 1/3, 0, 3. If this was log base 10, we would have 1/10, 1 and 10. If this was log base 5, we'd have 1/5, 1 and 5. Now, we got to get this to be log base 3 of x plus 1 plus 2. So that plus 1, okay, that plus 1. Riley P., what is that plus 1 doing to our function? Okay, so we got to move left 1, and then that plus 2 at the end. And Ms. Stock, what's that going to do?
It's going to move it up 2.
Up 2. Okay. Okay, so whether you do it numerically or on the graph, we have the coordinate 1/3, negative 1 that we need to move left 1 and up 2. So we're now at the coordinate negative 2/3, 1. We have the coordinate 1, 0. We need to move it left 1 and up 2. So now we are at 0, 2. And then finally we have the coordinate 3, 1. We need to move left 1 and up 2. Oh, make a little trail there. And so now we're at the coordinate 2, 3. Okay. If you like to think of this numerically, we moved left 1, so we subtracted 1 from our x's. Up 1 means we added 2 to our y values. Okay. Our asymptote, does it remain at 0? Okay. Where would it get shifted to? Okay. Since we had to shift left 1, our asymptote would also get shifted left 1. Let's talk about our domain and range. Domain and range. Nate, help me with the domain. What would you identify the domain to be?
Negative 1 to infinity.
Negative 1 to infinity. We have that asymptote at x equals negative 1, and we have graph to the right of it, so negative 1 to infinity. And then our range. Chelsea, how would you identify the range? Where do we have y values? Let's take a look at our parent graph. What did we identify the range for our parent graph? All real numbers. Okay. So look at this graph. What's our range here? All real numbers. Okay? The range for any logarithmic graph will be all real numbers. Okay? Now, one last thing we need to talk about with this example. The x-intercept. Okay? When I ask you for an x-intercept or a y-intercept, the process for your first step will never ever change. The methods we need to use to complete the algebra, that's what's going to be different from problem to problem, okay, when we talk about different chapters, okay? But x-intercept simply means we plug 0 in for y, okay? We plug 0 in for y. And I know we haven't officially talked about how to solve a logarithmic equation, but I think we have enough background to where we can figure out what our x-intercept is, right?
Yeah.
Okay, what would we need to do first?
Minus 2.
Apples. And subtract.
Okay. Yep, now we can do our switching around, right? We know that 3 raised to the negative 2 power should equal x plus 1. Well, 3 to the negative 2 power, that's the same as 1 over 3 squared, which is 1/9. And then we subtract 1 over to get negative 8/9. Look at your graph. Does it look like the x-intercept is at negative 8/9? Okay, then that's good, right? That's good. Make sure it's reasonable. So our x-intercept would be the coordinate negative 8/9, 0. When I ask for an intercept, I do want the coordinate. I didn't take off points on your test for that, but we need to get in that habit. Okay. All right, there we go. Your homework tonight.